Welcome to example number 5. We have a block that is on a smooth inclined plane. That means it has no friction. And the block starts from rest at the very top of this incline and then slides a distance of 2 meters along the hypotenuse of the triangle here. And we're asked to find the acceleration of the block, the speed at which the block reaches when it reaches the bottom, and then we want to also show in our work that the mass is independent. It doesn't matter what the mass of this block is, you'll always have the same answer. Okay, so this angle here is given as 15 degrees. And the first thing I normally do is I take a look at the body and I draw a free body diagram for that body. So in this case, the body we're looking at is the block. And let's draw all the forces acting on that body, and we'll draw them all from the center here. So go ahead and take a moment and see if you could draw the free body diagram for this block. Maybe you want to pause the video and then check your answers. Okay, assuming you've done it, you should have drawn a force of gravity going downwards, and then a normal force that is perpendicular to the surface. Now, after I've drawn the free body diagram, I think it's also important to decide on an appropriate coordinate system. So I'm going to choose to have an x-axis that is moving right along parallel to the plane, and then I'll have a y-axis that is perpendicular to the plane. So you can either draw it right on top of the diagram. I usually use a dashed line here, or you can show them over here on the side, for example, something like this. That's really up to you. But you do need to demonstrate it so that we're aware when we grade your papers what you're choosing as the appropriate coordinate system. Sometimes you might find it better to show it just separately over here so that we don't confuse your coordinate system with the force or the free body diagram that is drawn. Okay, so now we can move on to solving the problem here. We've drawn our free body diagram, we've labeled an appropriate coordinate system, and now we know that the object is accelerating downwards. So I'm going to show the direction of the acceleration right along the axis. And this is why I chose the x-axis along the incline, because when I apply Newton's second law, I'll be applying along the x-axis and I'll have the object accelerating along the inclined plane. So let's move on to part A now. The sum of the forces along our x-axis right here, the vector sum of all those forces, which is really just the force of gravity, the x component of that force of gravity, is equal to mass times acceleration. That's the mass of this block times the acceleration that it's moving at. Okay, now, so you're just going to rewrite this as ma, that's what the net force is equal to. This means add all the forces that are acting along the x-axis. Well, in this particular case, you really just have the force of gravity. So we have, I'm going to draw this in a little dash line here. This is the x component of the weight. And then over here, I have the force of gravity along the y direction. I've just moved this. This is the force of gravity right down here. So the component of the force of gravity that is causing it to accelerate is this Fgx. That's the component that is parallel to the plane. So this we'll write as the Fg sub x here. So this is the x component of that weight. Okay, so the next step is we're usually given what Fg is. We're going to now redraw this out, this little triangle here. There's the force of gravity, and let's now show the y component of that force of gravity. So there's Fg sub y here, that's the perpendicular or the y component of that weight. And now this Fgx, which is up here, I'm just going to move that over here so that I can make a right triangle. So I'm going to move it right over here now. And this is the x component of the weight. And remember, the x component and the y component are along the x and y axes, which are perpendicular to one another. Hence, these two components are perpendicular to each other. So this is a nice right triangle. Now, you're given an angle of 15 degrees. You know that this is a right angle here. So what angle do you think this would be? Well, you know that all the angles in a triangle add up to 90 degrees, or sorry, 180 degrees. And you know that if you have a right triangle, that these two angles must add up to 90. They must be complementary angles. It means that this angle is 75 degrees. 75 plus 15 gives you 90. Now, if you were to sort of draw a dashed line here, let me just move this out of the way. I'm just going to put another tilted axis over here, and that this dashed line here is parallel to this dashed line, and this is parallel to this dashed line here. So what do you think this angle is? Well, that's 90. So what does that make this angle out here be equal to? Well, hopefully you realize it's going to be 15 degrees because it'll be 90 minus 75. So you might be wondering, why am I doing all this? Well, it's because, you know, in here, this tiny little triangle in here, that angle right up here is exactly the same as that this is 15 degrees. Remember that the weight is going along this straight up and down direction, or down direction, and this y-axis is chosen to be perpendicular to the plane. So therefore, this angle of 15 degrees down here is actually that little angle up here in our triangle. And we need that because we're going to rewrite the x component of the weight in terms of the actual weight of the object. So if we were to rewrite fgx in terms of fg and this angle, you'd have to involve a trig ratio that involves this side, which is opposite to the 15 degrees, and then this side, which is opposite to the 90-degree angle, which is called a hypotenuse. And that involves sine of the angle. So sine of theta, or 15 degrees, is equal to the opposite, which is fgx, divided by the hypotenuse, which is fg. So therefore, our x component of our weight is fg times sine theta, or sine 15. So let's substitute this now into here over here. We have fg, that's the weight, multiplied by sine of the angle, which is equal to m times a. Getting very, very close now. One more formula you need to remember. The force of gravity is equal to m times g. So let's replace this now with m times g, sine theta, which is equal to ma. You may notice now the mass of the block cancels out. So therefore our acceleration due to gravity is just the acceleration due to gravity multiplied by the sine of the angle, that this angle of inclination in our plane. And notice, by the way, that the mass is canceled. So if we really actually answer part C, this line shows that it is independent of the mass. Okay, moving on, we can now substitute in our acceleration due to gravity would be 9.8 meters per second squared, and then multiply that by sine of our angle, which is 15 degrees, and this will give us an acceleration of 2.54 meters per second squared. Okay, last part. We've already actually done C, so we're just moving on to part B. So if the block started with initial velocity of 0 meters per second, and then when it gets down to the top, it has some speed, what is it? Well, then we're going back to what you learned in the earlier chapters. This is just really just a 1D kinematics problem. We're just looking at a block that's moving along our x-axis. So we know the initial speed is 0. We now know the acceleration is 2.54 meters per second squared. And we know that it slides a distance of 2 meters. So we know that delta x is 2 meters. That's along our hypotenuse of our incline. So what equation do you think we're going to need to use? This one. The final speed squared equals the initial speed squared plus 2 times the acceleration times the displacement. The initial speed is 0, so this term drops out. So our final speed squared is equal to 2 times the acceleration, 2.54 meters per second squared, multiplied by our displacement of 2 meters. And when you solve for v, it'll be the square root of 10.1457. That's going to give you, the square root of that is going to give you 3.1 0.85, or let's round that off to 9 meters per second. Just as a small aside, we could have asked you to figure out the normal force. But if I asked you to find the normal force, I would need to tell you what the mass of the block is. Now, how would you get the normal force? In this case, you hopefully are thinking of the sum of the forces along the y-axis. Now this block is only sliding along our defined x-axis. Along the y-axis, it's not like hopping up or down here. It's remaining stationary on our vertical axis that we've defined. So when you do the vector sum of the forces along our y-axis, they balance each other out and give you a net force of 0 along our chosen y-axis. So what forces are canceling each other out? That would be the normal force is balanced out by the y component of this weight. So as an aside, if we were to find out the normal force, we would need to find the y component of the weight, FGY. And FGY can be calculated over here, thinking of cosine theta, which is the adjacent over the hypotenuse, so it's FGY divided by FG. So FGY would be really just FG times the cosine of theta. So, or mg times cosine theta. So in order for us to find the normal force, we would need to know the mass. Okay, that's it for example number 5.